All right, so here I've worked through that calculation. So of course, as I said, we are going to use the chi-square test statistic, and here is the formula written over here again, in case you've forgotten it, which hopefully you will remember it for the rest of your life. And so we have the observed value for each of the genotypes here, 17, 55, 12, which sum up to 84 individuals. And then over here, for each of those genotypes, we have the expected value that we have computed using the Hardy-Weinberg equilibrium relationship. And we're dividing, of course, by the expected value. And then we have computed, when we square them and divide by the expected value, we've computed the chi-square value for each of those three genotypic classes over here. And of course, what we want to do now is sum up those chi-square test statistics. So if we take the sum of all the chi-square test statistics, that's equal to 8.282. Now let's think about what we're testing here now. Our expectation, remember, for the null hypothesis is that nothing unusual is going on. And Hardy-Weinberg equilibrium gives us an expectation of what the condition in which nothing is going on, what things should look like. And so in this case, we define our null hypothesis as the population is in Hardy-Weinberg equilibrium, and the alternative hypothesis is that the population is not in Hardy-Weinberg equilibrium. And that's what we'd like to test. So now we have to determine, given that we've computed the chi-square test statistic for these genotype counts that we see in this population, or the sample of the population, how surprised are we to get a test statistic that large or larger given that the null hypothesis is true? And so here's our chi-square test statistic. But in order to be able to interpret that, of course, we need to know the number of degrees of freedom. So what are the degrees of freedom in this case? Well, this is just like when we're looking at the different phenotypic classes in Mendel's experiments. We know that in this case, we have 3 different classes. Okay, so these are our 3 different genotype categories. These 1, 2, 3. And so typically, as we saw with Mendel's phenotypic proportions, or in general with the chi-square test statistic, the number of degrees of freedom is the number of different classes or categories minus 1. In this case, however, we lose 2 degrees of freedom, and we only have 1 degree of freedom left. And that is because we've lost 1 because of the requirement that the number add up to 84, and so we lose 1 degree of freedom from that. And the other place in which we've lost 1 degree to freedom, so we have n, so we lose that one, but also we computed p from the data, and so we lost another degree of freedom. We actually got q for free, because once we know p, we get q, of course, because that's just 1 minus p. So in this case, we've lost these 2 degrees of freedom, and so the number of degrees of freedom in this particular chi-square test statistic is equal to 1. And so we, of course, now would go and plug that into R, and you should plug that in and find out what the p-value is. I will tell you that in this case, the p-value is equal to 0.004, and so we could say that we're going to reject the null hypothesis given this chi-square test statistic, because we only have a probability of 0.04004 of getting a chi-square test statistic that large or larger when the null hypothesis is true, and so that's a pretty low probability, and so we have support for rejecting the null hypothesis. And so you can see in this case that in fact what we could also, if we investigate further, we could say, well, in fact, what we seem to have is an excess of this particular class. We have 55 heterozygotes, where we only expect 41 or 42 heterozygotes. And so it's this particular genotypic class that is inflated compared to our compared to what we would expect from Hardy-Weinberg equilibrium. And that turns out to probably be due to a very interesting phenomenon that I'll talk to you about later in this lecture, in which we actually get preferential transmission or generation of heterozygotes in this population.